I am a senior software engineer with Cincom Smalltalk, and this talk is going to be on HTTP2 support in Cincom Smalltalk in the upcoming version that has imminent release, 8.3. I would like to say, before I start, the HTTP2 protocol was very interesting and quite challenging to work on, but also very rewarding, because it kind of brought together a lot of things that I had previously thought about marginally and didn't have to really deal with it in my daily job. So from that perspective, it was also kind of educational to work on it. So let's just start. Here's a nice infographic showing you all the different things that HTTP2 can help you to achieve, and you will probably wonder, well, what's the big deal? We do these things today, but hopefully throughout my presentation you will see why it is kind of a big deal. So before I start talking about the more the technical and some of the experiential things with HTTP2, let me back up and give you a little bit of history. A lot of young people are here, so it never hurts to do a little review. So as you know, HTTP stands for Hypertext Transfer Protocol. And the first time the hypertext was used, as far as I could find, was in 1965 by Ted Nelson for the Xanadu project. And those who know Smalltalk history will also know that Ted Nelson was one of the people who worked in the original SiouX group that eventually developed Smalltalk. So strangely, it has that connection to our own language. It took only about 23 years before hypertext was actually used in the first HTTP and HTML implementation at CERN. And it took another 2 years before the first documented version was published, and that was version 0.9, which you can look up the original as implemented spec, because it was more after the fact, right? And then it took another 5 years until the first official version that was published as an RFC. Before I continue, I'll be quoting a lot of RFC numbers. Don't worry about those. They are just kind of, numbers we like to put on things, right? So the first version that was official was not really, because one of the things that you can read right at the beginning of the document is, this memo provides information for the internet community. This memo does not specify an internet standard of any kind, only if it were true. As you know, it did really become a standard. And just a year later, with small changes, the first standard was released as RFC 2068. And that was the HTTP 1.1 that we use until today. So we are basically 20 years later using, with minor tweaks, the same version of the protocol that was published back then. There were some updates in 1999, and then 15 years, nothing happened. And in 2014, HTTP 1.1 was split into 6 different specification parts, so they deal with separately with headers and with content types and all those things. No need to go into details. But only 1 year later, the HTTP2 was published as RFC 7540, and there is a link to that actual specification if you happen to have a problem falling asleep. Very good reading. So only about 2 years ago, we had the final specification of HTTP2 available for reading, studying, and starting to implement some of it. So, I'm sorry, this always happens in the least opportune time. Galaxy is my backup server for. Right. So before we continue, I would like to point out some of the HTTP2 protocol key points, because we may be coming back to that during my talk. So first thing, which is really important, is semantically compatible with HTTP 1.1. So you still have the same get, put, post commands or requests. So it's very familiar. The clients and servers really begin when they connect over HTTP 1.1 and they negotiate the upgrade of the protocol to the next level. So that allows the mutually unknown entities, basically, they don't depend on one another in terms of implementation. If one just does 1.1, the other one must conform. But if they do, if they both support HTTP2, they will both select that and upgrade. It has a fairly rapid adoption rate. Only 2 years after the spec was published, we already have quite a significant portion of major websites using the protocol. It has vastly improved page loading performance through several different mechanisms. Things like header compression, using server push technology, pipelining of requests, and stream multiplexing over a single TCP connection, and these are all things that I will be showing later. All the web browsers currently support HTTP2, but all vendors stated on the record that they are not going to support it over open connection. So only secure version over TLS. Okay, so here is the adoption rate I mentioned. Arden talked about some numbers earlier. Funnily enough, they are about a month or 6 weeks old. I looked it up just a few weeks ago, and the number actually went up from 15.9 to 16.4% of the top 10 million websites. And you can see the slight curve. It is actually roughly doubling every year. So the adoption rate is very fast, and below is the w3text.com website, which monitors and produces reports on these kind of things. How about the components of the protocol itself? It has some key elements, one of which is a stream. So really, when you have an HTTP2 connection, it is basically a collection of interleaved streams, which may be coming in both directions in a multiplex fashion. The next key concept, which is again very similar to HTTP 1.1, is request or response. And then there are frames, which are the smallest parts of HTTP2 traffic, and each message can be in one or more data frames with some control frames around it. So the different frame types are things like priority frame, header frame, continuation frame, and they actually allow kind of tuning of some of the performance characteristics for the protocol on the fly while the connection is already active and while data is in transfer. And the frames for different streams may be interleaved, and I will talk about why that is important a little later. So here the graphic here shows basically the top up. Oops, wrong button. The arrow here shows the traffic from client to the server. First you get the headers frame. There must be at least one header frame, but there can be multiple. And then they are followed by multiple data frames, last of which will have a flag that says this is end of stream, and that basically represents the end of the request message. And on the way back, the response message has basically exactly the same structure. So it's conceptually very, very simple. Okay, that's kind of the generic stuff. Now, how does it, see, I use that word again, stuff. Okay, how does it reflect in the Cincom Smalltalk SiouX Server? First of all, we had a preview in VisualWorks 8.2. It was work in progress, but we put it in the preview because we wanted to see if anybody uses it, if we can get any feedback and that sort of thing. And throughout this last release cycle, we worked actively on the full protocol implementation. So in the coming version of VisualWorks, except for very small little optional things, the protocol is fully implemented. We support both open and secure version. So even though browsers require that you use secure version, if you have an internal client-server application and you don't require any special security, which we won't go there right now, you can choose to use the open version of the protocol. Because of the security requirements, we also had to add some things to our own security frameworks. For example, as I mentioned already, HTTP over TLS is required by all web browsers. And some TLS cipher suites are explicitly required by the specification. This is basically to ensure that minimal level of security will be achieved when you use TLS. And so we had to add some authentication encryption with additional data, those types of cipher suites, and that alone was kind of another major project. And I'm going to talk about that in my security talk tomorrow. So as I mentioned, it was challenging but also kind of fun, working on things like stream multiplexing, prioritization and dependencies, but all these things which are required by the specification are there. As an example, I should mention a lot, or almost all, about HTTP2 is about two things: improved security and improved performance, and maybe even in the other order. So here is a comparison of header compression. In HTTP 1, your typical request, and this would be like a minimal request which does not have any extra special headers, would have, this is the post request, this is the path of the URL and the version of the protocol, who is the host, what is the content type, and so on. And so you consume 98 bytes. In HTTP2, look at the slightly different format of the headers. They all are lowercase, and some of them they start with colon. These are called pseudo headers, and they have special codes, so they can be really tightly compressed. You don't actually send over the method name or even the post because they have special codes. So this HTTP2 header is encoded in bytes, and you only consume 39 bytes. So less than half of it. And this may look like not a big deal, but network bandwidth is, even though we have fast networks, it's expensive. It's a resource that gets consumed. And when you have thousands and thousands of requests, this translates into some significant saving. So multiplexing is basically a mechanism that allows the requests coming over a single TCP connection in more or less not random, but interleaving order. So they can also go, like, you can send a request 1 and request 2 and receive the response 2 before response 1, which in HTTP 1.1 was not possible. So the traffic, as I mentioned before, is broken down into frames, and those frames represent pieces of the virtual HTTP streams. And each stream represents a request-response pair. So in this graphic here, you see, I guess I'm not very used to this device. You see the header for stream 1 followed by request data for stream 1, and then arbitrary, let's say 2 or n header. And then you can have data for stream 1 again, and then data for stream n, and so on. And as I mentioned on the way back, the headers for stream n, which came after header 1, can be coming before header 1. So this allows the clients and the servers to basically fine-tune how the traffic, in what order the traffic should travel. And a little later I will show why this is important. So the class that does all this work is HTTP2 Server Multiplexer. If you get the full version, the supported version of Visual Works, it's in the SiouX HTTP2 parcel. And the key differences are that between version 1.1 and version 2 is that in version 1.1, when you accept a connection on a TCP port, you create an instance of HTTP connection. It has its own process and its own corresponding request context. In HTTP 2, as I mentioned before, you accept a connection, you negotiate the upgrade, and if you do, you get an instance of HTTP2 Server Multiplexer, and after that, each stream has its own process and its own request context, but it all happens on the same TCP connection. So the difference is that you have much fewer TCP connections when you are using HTTP2, but you can have several processes per connection, and they basically they have the affinity to the streams. Now, obviously, to achieve something that I was showing you a little earlier, you need some kind of algorithm to determine what goes first and what goes second, right? So the protocol has prioritization rules where you can specify a weight that determines how much resources you assign to processing of a given stream, and dependency, which basically means you can block the processing of one stream until another stream is fully processed. Now, web browser support for prioritization is still kind of evolving. We have seen, as you get the automatic updates for browsers, we have seen that Chrome is ahead of Firefox for a couple of weeks, and then Firefox leapfrogs that, and it's still evolving, but the good news is that the prioritization rules are kind of add-on to the basic protocol, so it kind of fits nicely together. Here is a little picture of some of the prioritization. So here you see the stream A and B, they have different weights, which basically means that for every 12 units of resources, whatever it will be, like 1K or something, that get processed for stream A, you only process corresponding 4 units of those resources. The next column here shows dependency. The stream D will not get processed until stream C is finished, and kind of a combination of the different scenarios. And we have actually seen things like this in practice because a lot of browsers do that sort of work under the covers, that they assign different weights to different kinds of resources. Another aspect of HTTP2 is flow control, which is a credit-based system. The two parties, the peers, negotiate how much resources each side can have, and they advertise it to the other side. And it's up to the other side to respect that. So if I say that I only have a 4K buffer for my frames, the other side must keep that in mind and kind of schedule the sending of the data. It's really important on the server side, much more than on the client side, obviously. But these settings are highly customizable, and they allow the control of memory allocation for the read and write buffers, and even allow them to change on the fly, some of them. The server push technology, it was kind of interesting because we've had some experience with it from writing Apex, where we use both WebSockets and the event stream protocol of ECMAScript 5. But it's very different than that. Server push in HTTP2 replaces what people used to do as, or still do, as inline resources, where you have HTML code and you put pieces of style sheet definitions or JavaScript. So you basically have this one huge document, and you inline resources, because in HTTP1, what you save are those headers, right? That you don't need the headers because now that resource is embedded right in the HTML document. Well, server push completely replaces or allows replacing that, because on the server side, the application can know, okay, so I'm going to send HTML, and I know that sooner or later, the client will ask for some style sheet or some JavaScript, because I know that's how the application here is written. So why don't I just push those resources on the client right away, saving the extra trip, right? However, it's kind of fine art, as we found, so it needs to be considered carefully when you use it, and I have some links later in the slides to resources that are useful to read if you consider that. Here is how server push works. So you have data frames. I omitted all the other control frames and stuff, so we only have data frames and push promise frames. So when stream 1 receives frame 1, the server may decide, okay, because I know that I will send for this page.html, I will also send script.js and star.css, why don't I push these frames before I even start sending back my own data? And then maybe later the second part of the request comes from client to the server, and then the remaining data from the two different frames travels back. So it's that whole interleaving. This shows four arrows, but it's all same TCP connection. So here are some HTTP2 code samples, and it's all very easy, very small talky. We create a server, we say listen on a given port for HTTP. I'm sorry, for HTTPS connection, then add secure listener to it to give it the names of your certificate file and your private RSA key, and then you say use HTTP2 protocol and start the server, and that's it. Under the covers, what happens is you have some configuration things This is basically the default implementation we have right now. You can override it if you want. So the important part here is that when I talked about the mandatory cipher suites, you always need to include this. This looks kind of cryptic, but who has worked with our TLS framework will know what they mean and how they are used. And then also what needs to happen is that you set the version of the protocol to the v20, because under the covers we do some double dispatching, and the version object basically takes over all the HTTP2 parts. Alright, and here is some additional settings control where you can specify how many concurrent streams you can process. This will depend on the application, on your server, on your network, on different types of things. What is the maximum frame size and so on. Configuring server push is equally simple. First, you need to tell the version settings to enable push, so that's that part there. And then, in a response to a particular request, which in this case would be that page.html, you just say, okay, also give it preload the link, style.css, and script.js, and everything else happens automatically for you. Now, Adam mentioned Apex, and so the natural question is, how about Apex? How does it fit into the picture? And of course, the great thing is that Apex inherits all the functionality of SiouX. So it is very transparent, and it has some additional performance benefits. Apex is really great if you want to do single load page application. So your HTML loads only once, and after that, all data is rendered based on, or all UI is rendered based on some data that you send back and forth. But those are typically JSON requests, so the data is minimal. You don't need to do that constant loading and reloading of pages. On the client, the perceived performance may not be earth-shattering, but on the server and on the network, it has huge, huge impact. What Kott would not have a demo. So I have one that is based on or inspired by HTTP2 demo on Akamai. And the way the demo is structured is that you have an application, it's really static, doesn't do anything fancy, in two different iframe elements. One loads it over HTTP1 and one loads it over HTTP2. They are basically 400 tile images that are assembled together to make the final image. And the only difference between the two is how the listener is configured. Moment of truth. This is the screenshot just in case the next step doesn't work out. This is HTTP1. And as you can see, we are coming to about 10, almost 11 seconds. Over HTTP2, we are down to 5 seconds. So, big deal. Twice, good, but great? I don't know. What do you think? Well, I think it's fantastic, because what that didn't show you is what the next slide shows you. Those 10 seconds, this is from another experiment we did in our lab. So the numbers naturally change depending on network conditions and so on. So what you can see on top are actually 6 connections taking 10 seconds. What you see here is a single connection over HTTP taking 1.5 seconds in that particular experiment, which means that in terms of bandwidth use and the network time we have spent, We spent 60 seconds of network time producing that first image, and we spent only 1.5 seconds on the HTTP2. So it's about 40 times increase in performance. So clearly, HTTP2 is a winner. So, as I mentioned, it's all about performance. So here are some of the HTTP2 best practices that we have either observed or found online. First is don't concatenate files. A lot of people do, okay, I need jQuery, so I'll grab all the pieces of the jQuery library, put it into one big JS and then load it. It's perhaps not the best example, but you get the idea that if anything changes in the smallest way in one of the components, the cache on the client has to be completely invalidated, and that is actually quite expensive. So HTTP2 allows you to completely not to do that. That was an optimization technique for version 1.1 of the protocol. Don't inline assets. I already talked about that. That's basically a special case of concatenating. And if you need to do something like that, use the server push if or when it is appropriate. Minimize the size of HTTP requests and responses, and that is, of course, always kind of the rule of thumb. The less data, the better. So you use data, JSON, whatever, which means use Apex. Right? Naturally. Well, it turns out nothing comes for free. There are some issues, but they are not specific to Sue. They are more, the cost of making that protocol so performant. One is that any server will have increased amounts of memory, because as you multiplex the streams, you need to hold more data in memory at the same time. Even though your CPU may be better utilized, you may use more memory. Because you need TLS and security certificates, it adds that extra element of complexity where you have to manage the certificates on your server and make sure that they are current and all those things. Those who use maybe Seaside or any other back-end web server technology are used to work with proxies, where, for example, Apache web server would act as a reverse proxy for your back-end application, maybe doing some load balancing, things like that. Well, unless things changed in the last few weeks, Apache must be built from source. You can't use pre-made binary because you need to explicitly enable HTTP with some switches on the compilation in the command line. And the trickiest part, which I'm really curious how they will eventually work it out. In HTTP 1.1, proxying is easy because you are acting basically as a man in the middle, right? You receive a request, maybe do some little massaging and send it on the other end. Well, with HTTP2, if it's over TLS, you can't do that because you don't have the certificate information that the actual server has. So at this time, the Apache module for HTTP proxy is still experimental. We will see how it will work out. And the last issue that I personally found really, really challenging, because I like to look at the network traffic. I start up Wireshark or TCP dump, and I can see the traffic. I can capture it, I can analyze it, did all the data come through the right way? Well, if it's encrypted, what do? You see the handshake, and after that you have gibberish, right? So that's kind of a challenging part to work with. So in conclusion, and I did not even use my time, so maybe I will show some other. In conclusion, the two versions of the protocol are semantically compatible, that's good news, but they are vastly different in specs and in implementation. HTTP 2 provides impressive performance gains as well as optimization options on the fly. Security is built in because it's forced on us by vendors. And the API for SiouX is very simple. We did a lot of work under the covers, so your API is basically just, okay, this is what I want to do, turn it on, boom, done. And of course, we will continue to work on additional enhancements and performance optimizations and those all those good things that we are proud to continually work on our product. There are some additional resources. This will be online, I understand. So these are actual live links, and if anybody considers using server push, I strongly recommend to read that very long URL document because it talks about some of the pros and cons and the best practices. And of course, the last thing is the demo, the one that you already saw. So let me just play it once more, see if you get the different numbers. Maybe some of it has been cached somewhere between Cincinnati and here. Doesn't look about the same. And HTTP 2. Right. So if you have any questions about the product, you can talk to any of us here at the conference or via email later. Yes, Annick?
Did you try to do load balancing using metrics and SiouX?
It's next on our list of things. Yes, I have actually looked at that just in the last couple of weeks. And we know that Matrix has some improvements that we need to do in terms of performance, but also in terms of security. So it's almost like one of the first things we will be looking at in the next release cycle. And I was actually intrigued by Bob's talk about using polycephaly on the back end because it's kind of similar scenario. Yes?
So, first of all, really good job. I think HTTP 2 is really important, and we're looking at ourselves at the and so I'm just curious, you said the memory was a little bit different, which I would expect. But what I'm not sure about, and I wonder if you've ever benchmarked like the HPAC, the header compression stuff, did that cause any spikes with CPU usage? It probably depends on the type of data, I would guess, but did that do anything to your...
That's an excellent question. Well, the HPAC compression is really efficient. It's not that we haven't seen any spikes on single or small number of connections, but we've had limited time to do any performance analysis, like load testing and that sort of thing. So.
I guess it would depend on the type of traffic, but yeah, I was curious.
It totally depends, because you have two different types. You have the pseudo headers, which are really, really efficient, right? And then you have some static tables. And here's an interesting bit, because before the conference, we are like, okay, what am I going to mention? What am I going to leave out? And my colleague, Tamara, was like, I'll leave that whole static and dynamic table out. Nobody cares about that stuff. But it turns out to be really important, because that is where you can tune out which of the headers are compressed and how much and how the whole Huffman table looks like and things like that. It's a talk for a large beer and long night. Yes, Georg.
Yeah, you were mentioning the young people, which only rarely are in the room right now, but my impression is that you belong to them, because you forgot in the list of hypertext systems the Smalltalk system of the early mid-80s called the Analyst, which was a hypertext system, written by Xerox in Pasadena. And so maybe next time you...
So, yeah, I am young because at that time I was a student at Charles University in Prague, and the only thing I could read about America is how it's up to destroy us. So. Sorry. Next time I'll get born somewhere else. Right? If there are any more questions, this is my dog Cindy saying, really? Okay. I guess we are done now. Thank you very much.